Okay, folks, today we're going to be starting chapter 6, which deals with all things electromagnetic radiation. Now, before we get worried about that radiation word, electromagnetic radiation is actually just light. Now, it's not just the visible light we see, it's not the colors that we're seeing on the screen here. It's also the infrared, it's also the ultraviolet, it's X rays, it's gamma rays, radio waves. There's a whole huge spectrum in there, and they're all dealing with waves because light, it is a wave. We're going to see proof of this here in a bit, but we have a few things that we talk about with regard to light. So we have the wavelength, which is what we're seeing right there, which deals with the distance from one peak to the very next peak. And it does vary. We have a whole bunch of ranges of wavelengths that we see in the real world. We can counterbalance that with the frequency, which is this little v. It's the Greek letter nu. And the frequency really is how many waves do you go through in a given time, or 1 second. And that's what they're kind of showing here. They're showing that you could actually physically count them, and then the frequency would be the times it goes through. So we have wavelength that will be measured in meters. Oops, I touched the screen, but I didn't turn on my pen. So we have the wavelength, which is the Greek letter lambda, which is going to have units of meters. And we have the frequency, which is actually per seconds, or S minus 1, or you'll sometimes see it as Hz for hertz. Both of those are interchangeable. Now, fortunately for us, doesn't matter what the wavelength is or the frequency, if you multiply them together, you always get the exact same thing, which is the speed of light. I gotta stop dragging my hand across my thing. Now, speed of light, and I'm going to put it down here with this equation. Now, it is something that's provided to us, but it is 2.99792 times 10 to the 8th meters per second. Now, the only thing we really have to worry about too much here is often the wavelength, the lambda, is going to be in different units, and that's because these get really, really big and really, really small. So nanometers are typically what we measure visible light in, and we'll see all that. So you might have to change the units for the lambda when we actually go to utilize it. All right. When we talk about light, we now know for sure it's waves. That's what this little picture is trying to show us. If we actually think about this as that Pink Floyd Dark Side of the Moon album cover, when a pure beam of white light hits a prism, because the wavelengths diffract differently, we actually get that weird little rainbow effect. And that's what this picture is showing. It's showing that turning into a wave. Now, early scientists, in order to prove light was a wave, they had to do some experiments. Now, everything on this page is actually a wave. It is an electromagnetic form of electromagnetic radiation. The gamma rays here on the far left are the most dangerous because they have a huge amount of energy to them. X-rays are as well. Now, both of those, what makes them so dangerous is the energy in those particular forms of electromagnetic radiation is so high that it can actually cause electrons to get knocked off where you're not supposed to. Gamma rays can actually cause the mass of the nucleus to change ever so slightly when it gets absorbed. Now, the others are, for the most part, relatively safe. We can't get too much ultraviolet radiation. That's what the sun does to us. That's why you hear things like skin cancer, and it will damage your eyes. But once we get down here, it takes a huge amount of these guys to actually do any danger. Now, there's certain ones that pick up because technically microwaves are just radio waves. They just happen to do a really good job of exciting water. Now, this picture is going to be exactly the same as the one you find in your textbook, with the exception that this will be right. Because if you notice, it's got red here on the left. It should be blue on the left, like it is down here. So it's just a little glitch in their image, at least the one I grabbed for this slide. All right, now on to how we proved light was a wave. For sure, guaranteed. Now, what we did to prove this, we used this technique of looking at the interference patterns that light gets when it goes through little small slits. Now, these are specific slits. They're actually very, very close together. And it says electron beam gun right there. That is going to work with electron beams. It's going to do the exact same thing. But this needs to be a monochromatic light. If you use a light bulb, you're going to end up with just a beam of light across here. But if we use something like a laser, like you notice how this is that nice red laser color, if we'd actually hit those two slits with a red laser, we get this interference pattern. And technically that proves that light is a wave. All right, I know, it doesn't look like that. How it proves that, we got to actually think about if light's a wave, we could actually view it from the top down, maybe something like this. And imagine each one of these lines is the top of a wave. And therefore the bottom's not drawn, but it'd be like directly between every single one of these lines. All right, so when it goes through these holes, the light actually will start to diffract. And we know it happens this way. I mean, if you think about it, you're in a dark room, but there's a window. When the sun hits that window, the light goes in all directions. It does give a very nice bright spot directly from the light source to where that window would be, but it also diffracts out. And that's what they're showing. The light actually will spread out from that hole. Even though it comes in, it's going to spread out. All right, well, what happens is when these two light waves interact, they're going to actually constructively and destructively interfere with each other. Now, what I mean by that, if you think about right along here, you can imagine peak of a wave, peak of a wave, peak of a wave, peak of a wave, peak of a wave. At those points, along that line that we could form by putting those together, these are right at the peak of both those waves overlapping. So those two waves are going to amplify each other. They're going to build up. They're going to constructively enhance each other. And right here, you see we get a much, much, much brighter spot. All right. That can be counterbalanced with a weird little other thing that we're going to do. So I'm going to erase that line I just drew because it's now in my way. And what I'm going to do instead is think about where the bottom, so right directly between here would be the bottom of the wave. And I want to think about where the bottom of a wave, for instance, overlaps with the top of a wave on the next. Because top overlapping with bottom, they would kind of cancel each other out because they're out of phase with each other. So right there, and then right here, so dead in the middle, but so middle of the two and peak of the wave, middle of the two and peak of the wave, we have another nice little straight line going. But if you look here, it forms a very dark spot. So it's canceling it out. The dark spot is because the two light waves, even though it's light, they're actually out of phase with each other and they lower those waves. All right, turns out the only way this happens, the only way this works is if light is a wave. So this is concrete evidence that we actually have light behaving like a wave. As a matter of fact, on this next slide, I have a little picture. It's a computer model of what would happen if waves hit that object. And if you notice, we're seeing that overlap. Now, unfortunately, that video will not play again, so I have to back up and then do it again. But as it goes through, the light forms those overlapping things, and you can see those interference patterns forming as it goes through. And that flat out is just a computerized model. It's not like we took a picture of a light anything hitting an object. It's a computerized model as if that big white ball we see there is just a wave. And it hits and goes right through, just like our theory predicts it. All right, so we got proof that life's a wave. And more importantly, when we actually look into it even more, we know it's what we call a standing wave. Now that's going to come in a little bit more important later, but all a standing wave is, think about this as a jump rope. If you're swinging a jump rope, it has, you got two people standing either end, they're almost holding that rope stationary. They're just whipping that to put some energy into it. And if they whip it harder, they get that little node in the middle. You've seen that when you're spinning a jump rope fast enough, it's got a little part in the middle that seems like it's not moving. Well, light does the same thing. We know that all light does this. It actually seems like it has like almost what you might consider a start point. It's at least a point where it's not moving. But all light is standing waves. All right. We can see that visually with sound very easily. Now, what this is a weird little thing. So on that black powder is just like carbon dust or charcoal powder. It's just a black powder. Now, underneath it is just a speaker, but instead of a standard speaker cone, it's a piece of metal on top of it. So that piece of metal is just going to vibrate like the speaker would be. And then I know it looks like there's fancy little probes. These are just wires going to a tone generator. Now, this is the same type of tone generator we would have all experienced in elementary school when they did the hearing test. So it's just those high-pitched tones. And the numbers on here are just the frequency they're running the tone. So it's very fixed note, very specific tone, and then they play it through that speaker. And what you see is the powder is moving around on there and building up where the sound waves have nodes where the sound is a standing wave. It's just a great way of visualizing it. Matter of fact, if you look on these on the internet, you can find where people made coffee tables out of this. So you know how you ever seen that where they actually get like the little rake and they rake nice straight lines in sand. Well, there's weird people. I don't know. I think it's just kind of neat. They've done that where it does it automatically. They just play a tone through it. The sand moves itself, and then they turn off the sound, and they have arranged their sand. Weird, but I still think it's kind of neat. I think I'd like to have one of those weird coffee tables. All right, so light's a wave. Let's look at something kind of interesting that we're going to do with these waves that going to actually add some confusion to the nature of light. Now on this slide, we have a picture of the light that comes off the sun. So that's what this yellow background thing. And it almost perfectly matches this curve that we get if you heat an object up to right around 5,770 degrees. Now, the curve in the background is not a real curve. Turns out we can't get a perfect black body spectra, and that's mainly because we don't really have any perfect black bodies. I mean, even something painted black does reflect light in some degree, and a black body would not be able to reflect light. So that gray curve is a theoretical curve. Now, we can get close to it with a few little outliers, but not much. Now, the biggest reason the sun is an outlier is because the surface of it is covered with hydrogen, and even though the heat is causing all this thermal radiation to come off, the hydrogen is causing certain reflections to occur, which cause these peaks to change. But it is a tremendously neat thing. Now, it turns out we can reproduce this color. So the sun's color can be almost perfectly reproduced by getting any object up to almost that temperature, 5,700 degrees. Matter of fact, if we go to some hardware stores, most of the time you'd have to look on the internet for this stuff. Our modern day LED light bulbs will have temperature listed on them. Now, they don't really get that hot. We don't have light bulbs. I mean, if you think about it, this is along here. These are what we might consider almost white light. But they don't get up to 4,000, 6,000, 7,000 degrees. That would actually make them quite dangerous. They mimic that just to get the color balanced right, because most LED bulbs actually have internally a mixture of red, blue, and green diodes that are actually just balancing out to get the color right. But the whole point of having those temperatures on light bulbs is so you knew if you buy one, when you go to the store the next time, you'd want to buy the exact same temperature so the color would match up. Otherwise, you end up with LED bulbs that don't actually have the same whiteness to them. Some are more yellow, some are more blue. There's even some that are more red. But that's all that temperature scale means. Now, it's interesting. If we were to get an old style incandescent bulb with the little metal wire in there, and we did get to these temperatures, this is the colors they produce. So a little orange glow would be something that gets that metal up to 1,000 degrees. And if we get it up to 10,000, it's a bluish white. So that is reflective of the color they get. And it doesn't matter what metal it is. Technically, to get this bluish white, we just need a metal that you can get up to 10,000 degrees and doesn't melt. Easy enough to get this. That's most metal that's reasonably strong can get up to 1,000 degrees, and it won't matter the type, but they'll all glow the same color. And we've seen that. If you think about it, a hot piece of wood in your fireplace, the metal on your stove, when it gets up to about 500 degrees Celsius, it starts to glow, and it glows that red. Well, what we're seeing is what we call blackbody radiation. Now, a pure, perfect black body is going to do something kind of cool. If we heat it up, so imagine these little blue lines are light photons being that are leaving it. And weird thing is, I got this arrow backwards because what I really want to see is this one arrow is going out through this small little hole. Well, that light is going to go out, and that's the light we're seeing emitted from a black body. Now, if it's a perfect black body, any of these other light beams that actually don't go out that hole are just going to be perfectly absorbed. There's not going to be any reflection. But there is no such thing as a perfect black body because to some degree, let's imagine this photon goes here. That surface might reflect some wavelengths of light. And if they happen to reflect and come out, that red line is actually adding to our black body radiation it's not supposed to. So we would get a spectra more like this that's not perfectly on that curve. Now we have some that get really, really close to getting that gray curve, some black bodies, some types of ceramic and some carbon species, so carbonized steel will get close, but nothing's really perfect. But it's perfect enough that we were able to get curves close enough to this, even back in the 1900s. So once we have those curves, what we're going to do is vary the temperature. Because, you know, I have this when it says it's at 5,777 degrees, yet we all know that any object up to about 500 degrees starts to glow. So what does that curve look like at 500 degrees Celsius instead? And that's what the 1900 scientists were doing. They're starting to look at it. Here's an idea of what these curves that they were able to obtain with. And we're seeing that color shift. Now, anything below like 5,000 degrees Kelvin, we're seeing mostly red light. Now, even though the peak's way down here in the infrared region, we don't see any of that. So we're seeing this little small portion that's actually red. And since that's the largest point in the visible spectra, that's the color it looks. And that's why it's up to 5,000 degrees before we start to see that get a different color. And obviously, it's what they're saying here is at 6,000 degrees, it's closer to a yellowish green in color. But we have this change. Now, this is actually based on experimental evidence. We actually are able to measure nowadays how much heat or how much thermal energy is coming off of anything at room temperature. It is way out here in the infrared, but all things at room temperature are giving off a certain amount of blackbody radiation. Obviously, they don't have a color. Matter of fact, we now know that we don't start to see a color until about 500, and the actual first color most people see is actually gray. And that's because it's such a low intense light that your red receptors, so the receptors in your eye that see red light, don't detect it, but your ones that see light, as in just black and white, so intensities, they would pick it up, but your body, your eyes would interpret it as a gray light. But as soon as it gets to be about 500 degrees Celsius, suddenly you'll start seeing red. Okay, so our goal for the early scientists is to figure out and predict what's going on. Now, at first, they tried to compare the motion of the waves, or the waves we're seeing, to a harmonic oscillator. So the thought process is this. I'm going to back up to our black body. What they're thinking is, along the surface of our black body, on those atoms, there's something in the atoms, like a spring, that's oscillating. It's bouncing up and down. And by bouncing up and down, that creates the oscillation that we see detected as light. So something's causing the energy increase to cause these springs to get more and more bouncy, and therefore we see more and more energy. All right. But when they try to apply this concept to an atom and use all classical theories that they can, when the scientists were able to map the high frequency or low temperature stuff, so the curve that's not really on here, so a curve at 298 degrees room temperature, they were able to map that relatively well. But as soon as they went up to anything reasonable, you get curves like this. So 5,000 degrees Kelvin, the curve's supposed to have a peak right in that yellowish green, and yet the harmonic oscillator theory has it go into almost infinity long before that, and it doesn't come back down. It doesn't actually show it coming back down to zero at all. It just goes up and up and up forever. Now, early scientists saw this and they knew it's wrong. There's no way it's right, because if this was even close to right, here at room temperature or at 5,000 degrees Kelvin, if this is the curve, this is bombarding the Earth with so much infrared that the Earth would have burned away long ago. So there's no way the sun is doing that. All right, so we have to come up with a new theory. Classical mechanics do not work on explaining what's going on with that black body radiation because they really don't show this drop off. All right, the person who figured this out is his name is Max Planck. He did it in 1900. Now we're not going to look at the full equation he came up with because his full equation perfectly matches any one of these curves we're seeing at the temperature you plug in. But we don't need to know the full equation because it doesn't really help us understand what's going on, and it doesn't really show the problem he created. Because having the curve is one thing. He created a weird little problem for early scientists they had to come up with. So all he actually did was he assumed that the frequency was related to the energy. He has this nice little equation, and it's based on an assumption that for some reason the energy doesn't go up to infinity really, because the frequency doesn't really go up to infinity, at least apparently not in the real world. There is a limit to both these, but they're somehow related. So what he's saying is the energy is proportional to this little constant he made up and the frequency of the energy that's coming off that. Now, that's all well and good, but the technical problem that all those early scientists were concerned with is that it actually puts things into a limit, as in energy can't go up in huge amounts. Or how about we think about this? If I back up to this harmonic oscillator, early scientists were thinking that the intensity we're seeing when things got hot like the sun was because this spring got really infinitely big. Well, Planck's saying, no, that's not what happened at all. On the sun, the reason it's so bright isn't because there's a really, really big spring. There's just a lot of there's just a lot of the normal spring. So the light photons we're seeing coming off the sun are the same things you're seeing on the screen right now. That's white light that has all those wavelengths in it. But what we're seeing now on the screen is much, much, much fewer springs or much, much fewer oscillators creating those sounds. He actually said it's smaller amounts. And the only reason the sun's more intense is because there's a lot of those small amounts. But he quantized the energy. He said it's only available to come off in certain packets. And that is the groundbreaker that actually caused some confusion and misunderstandings and reason that a lot of people thought he was wrong at first. Because it doesn't make sense to say that light is coming off in packets, because if energy's quantized, the light would have to be quantized as well. And that actually created some problems. All right, fortunately, there's this other guy, Einstein, that steps in and he's able to explain this photoelectric effect using that quantized energy. So, all right, so what the photoelectric effect is, and that's what this picture's showing, and there's a reason it's red, green, and blue. Well, purple. What's going on here is when light hits a piece of metal, and it's the right type of metal, it can cause electrons to be ejected off that metal. Now, varying that piece of metal changes how it reflects, how the electron gets kicked off, and Einstein was able to figure out how to predict it and use that for something. So what he found, though, something interesting. Notice how wavelengths is 700 nanometers and then 550 and then 400. So the wavelength is dropping as we go from left to right. Well, at 700 nanometers, no electrons were ever ejected, but at 550 there were, and at 400 they were. Well, what the early scientists were having problems with is they could make this 700 nanometer light much, much, much brighter. Matter of fact, that 700 nanometers is coming off the sun. If you could somehow isolate it, sun's really bright, that would be a really, really intense light. They found out if it's at the 700 nanometers, it didn't matter how intense it is. And intensity would be just, a larger wave. Well, it turns out it didn't matter if the wave was big. It didn't matter how the intensity is. if the frequency or if the wavelength was, in this case, too large, nothing ever got ejected. So Einstein was able to show that it's the frequency that's important. So inverse these. Remember how our frequency and wavelength are related to the speed of light? So if my frequency goes down, or if my wavelength goes down, frequency is going up. They go opposite. So this has got the highest frequency. Well, what Einstein did to explain this was he looked back at Planck's work with that energy is quantized. Energy is related to the frequency of light being emitted. And he said, well, this is kind of like the opposite. So the blackbody radiation talked about light being emitted. This is talking about light being absorbed. And what he was saying was that energy packet being related to the frequency has to be a certain size. So this photon of light is too small to cause the ejection of the electron. It doesn't have enough energy in it. But as soon as I lower that, or as soon as I increase that frequency some, go from that red to that green light, suddenly this has more of a frequency. Therefore, this wavelength has more energy. It hits it, and the electron gets ejected. Well, Einstein, in all his cleverness, was able to come up with an equation that explained all this and even actually told us how fast these electrons would be leaving. And it was always related to the frequency. And the other cool thing is his equation actually had Planck's constant in it. So even though he wasn't dealing at all with blackbody radiation and light being emitted from an object, he was able to show that Planck's constant was actually explaining the photoelectric effect. All right, so we have a small problem in the 1900s when this is going on. We have this wonderful little duality issue. Light must be a wave because that's the only thing that explains interference patterns. And it also must be a particle because that's the only way that you can really explain the photoelectric effect. Turns out light's both. It has particle and wave-like properties. And sometimes you can actually do the calculation totally as if it's a wave. Sometimes you can do the calculation as if light is totally a particle. And sometimes you can choose both ways and you'll get the exact same results. All right. So that introduces some interesting little conclusions we have to do with regard to light. Now we're going to look at a few other things, but before we do that, we're just going to do a nice little calculation to see how we do this. So this one just says, what's the energy of a photon that was emitted when the with a wavelength of 640 nanometers? All right, the two equations we're going to need for this. We have Planck's constant, which is what we're going to use to give, or Planck's equation, which we're going to use to get our energy, because it asks for the energy. And that is just Planck's constant times the frequency. If I didn't give you frequency, I gave you wavelength. So we're also going to use the relationship of the speed of light with wavelength and frequency. And I'm just going to end up combining these because I'm actually going to rearrange this to solve for V. So I'm going to see that what I'm going to plug in is E equals H, and instead of that frequency, I'm going to have C over lambda. Speed of light over lambda. All right, so got a cool thing going on here. Energy equals, you will get Planck's constant. It's on the, it'll be in the instructions on your quiz, so you don't have to actually have this memorized. 6.62607 times 10 to the negative 34th joule seconds. And put that in parentheses. Right next to that, I'll have the speed of light. I had that up here before, but that's 2.99792 times 10 to the 8th meters per second. And wavelengths going on the bottom of this thing. And I can just do this. But my wavelength I gave you is 640 nanometers. We need meters to get it to cancel out. So I'm going to have one little more conversion. 1 meter is 10 to the 9th nanometers. Nanometers will cancel, meters will cancel, seconds will cancel, and my final answer is going to be in joules. All right, do practice this type of thing, or this type of calculation, because knowing how to put all these exponents into your calculator and how your calculator handles it is kind of important. And If you are doing the practice test on Canvas, I'll make sure that I have good directions on what kind of calculator to suggest, because I guess I can't make you use the honor lock calculation. I'll have to see what I can do. There'll be instructions on the practice test. So -34th. And I'm using this EE button on the calculator. So if you're using a TI, that's a great button to use. If you're using a TI that has times 10 to the nth, right, it's right around where the stat button is on that calculator. Put this whole thing in parentheses, and that'll make sure the calculation works. But if you have the EE, you can just put it in just like I'm doing. So times 2.99792 times 10 to the 8th. And then we'll divide all this by 640. And then divide is times. So times 1 times 10 to the 9th. And I get that this is a very small number, but we are talking about the energy of a single particle of light. So it's 3 point, and I'd only have two significant figures because that's 640 nanometers I've written it. So it's just 3.1 times 10 to the -19th joules. All right, next little thing we're going to look at. We talked about Einstein and Planck were telling us that light gets emitted and light gets absorbed, and somehow that light gets turned into energy. And this was kind of like blackbody radiation. This is how it's being absorbed. So this is the photoelectric effect. But we found out when we're getting away from those black bodies, pure elements and pure molecules only give a small spectra of emitted lights, and they also only give certain ones that they absorb. Now, on both this page, this is just hydrogen. So if I actually had a sample of hydrogen in a gas and get enough energy to it, it just emits these wavelengths. If you run that through your dark side of the moon light prism, you'd have just these 5 individual lights. And if we were to somehow shine light on it in all wavelengths, we would find that just those 5 get absorbed. Well, it turns out no matter what we do, all substances do something like this. That's how we make neon lights. Now we call them neon lights. Turns out, I think neon is like an orange color. So that might be neon. That looks awfully yellow to me on my screen. But neon is actually an orange color. Other gases are used to give color, other colors. Like the hydrogen the hydrogen most part comes out looking kind of red. Some people think it's pinkish red. But you have different gases in there, give different colors, and we got this wonderful breakdown. So I grabbed this out of your book, and this has got certain pure elements and the individual waves they give if we run them through that spectra. All right. Now that we know that's coming off the atom somehow, we want to try to explain what's going on. So we want to try to find a pattern to this chaos. And we want to find something that would apply to all atoms, at least with some minor modifications. All right, way too complex. Somebody very smart figured this all out. And matter of fact, he realized he basically was good at looking patterns. So let's look at hydrogen, which is our simplest thing. He probably noticed something along this line. If you notice, this gap is small. We get a slightly bigger gap, and we get a slightly bigger gap. And if we back up to that other spectra page I had that had a 5th line, we see that every single drop gets closer together as we get more and more close to the ultraviolet frequency. So there is maybe a pattern based on that. Well, our smart guy, Rydberg, figured out the pattern. And it is related to this wonderfully long equation right here in the middle. Now, I say wonderfully long, but look at that. Got this crazy big number here that's measured in per meters. But what he found was something kind of neat. If you had this equation, you could actually map all those frequencies that we see for hydrogen, all those wavelengths, and they're just related to this crazy big number and then just integers. Matter of fact, every single one of these frequencies measured in their nanometers, or they'll be measured in meters and you'd have to convert them, those all come about if we actually plug in a 2 right there and then just something bigger than 2 here. So 3, 4, 5, 6, and 7. Those sets of numbers would give you all the wavelengths for those lines we just saw. So Rydberg showed us something very, very interesting. Even though this all looks like kind of chaotic, because there just seems like these lines are kind of random, he was able to show that they're all related to integers. And it's related to something, or how we were talking about how light is based on an oscillation on the surface. Well, this oscillation is going from like a state of 2 to 3, or 2 to 4 to 2 to 5. Now we have no idea what the 2 and the 3 are, but they're fixed integers. The wavelengths are related to just flat out integers, not fractions, not weird numbers, flat out just integers. Now, as neat as that is, when you get in and look at the hardcore math he came up with to come up with this crazy number, you find out that Planck's constant is in that value. So this somehow, even though it doesn't look anything like it, it is related to Planck, and his energy equals Planck's constant times frequency. So it bridges all these together. They're starting to get close. Now, this is finally coming up with something really cool by this guy in 1913, Niels Bohr, combined all of these then to one theory. I see I got this messed up already. That should be raised, so it's 2.18 times 10 to the negative 18th. That's an exponent up there. It's not actually raised for some reason on your side. All right, but this would actually calculate the energy it takes to move from a level 2 to like a level 3. So that's what we're talking about here. So if I want to talk about light being emitted, we're talking about something coming from a higher number and dropping back down. If I want to talk about being absorbed, it's at a lower level going up. But this will actually take care of it. It would actually pop it in. And any of these ends are just numbers. Matter of fact, Bohr said it was something like this. We have just these little integer levers, and they go from 1 up to infinity. They do get really, really close above 5, so that's why infinity looks like it's really close to 5. Whatever these levels are, they get ridiculously close as they go up. But what we're seeing when light's being emitted from an atom, so if we put energy into an atom and it gives off color, we're taking something from a lower level and moving it up. But these levels are just integers. And I know they don't look like they're evenly distributed here, but it turns out Bohr's little equation on this does actually map all that stuff out. So the gaps are closer when these ends are closer. And that really is, if you think about it, you square a small number, it gets exponentially bigger. So that's why these get further apart when we're very, very low. Okay, so even though Bohr bridged all this together, he was able to show that this number was built off Planck's constant. So these are all these little things, all these little equations we've shown are all related to one another. You can trace the path from Bohr back to Rydberg to Einstein to Planck, and they all actually are saying the exact same thing. All right, but Bohr's model tells us something interesting, that there is a low ground state. Now, in the atom, we don't say the ground state is at 0, because even in the ground state, the atom's exhibiting some energy, because there is a ground state that doesn't involve the electron hitting the nucleus. So the electron is orbiting the nucleus, so the ground state doesn't have a 0 value. Lowest value is 1. As we go up in states, we just move that number up a letter. So it goes 1, 2, 3, 4, all the way up to infinity. And anything larger than 1, we actually just say it's excited state. All right. Now, once we explained all this and actually came up with this equation, Bohr was able to show that that equation worked for any atom that has just 1 electron. So we can't really study this a lot, because the only atom we have on the periodic table that has just 1 electron is actually hydrogen. So Bohr's model was sometimes called the hydrogen model. But it turns out we actually can study helium. But it needs to be helium ion, where we've ripped an electron off. And we actually can go up one more on the periodic table to lithium and study it. But we need to remove 2 electrons from lithium. Now, reason those exist is because we actually can rip that many electrons off those guys without too much trouble. And as long as they have one electron, they actually fit Bohr's model. So it is kind of interesting. Bohr is considered one of the great scientists in the early quantum theory, and he made a model that worked for one atom out of 118. Kind of cool, huh? All right, but it gives us something to start with. Now, the reason it doesn't work for anything else can be kind of illustrated with this. We'll come back to that in a second. This crazy picture here. Now, what I have here is a picture of water hitting, drops of water hitting water. Now, the reason that's showing it is because we are talking about waves, and water is a great way to visualize waves. Now, on a hydrogen atom, we pretty much have a single drop hitting a surface of water. The ripples, the waves will go out, and we can very easily predict that we're going to have concentric circles going out from where that drop hits. Every other atom has multiple drops. Those overlapping waves are going to interfere with each other constructively and destructively. The fact that helium has 2 electrons actually creates a little bit more chaos. And that's going to be, actually, we're going to bridge that into quantum theory to explain what's going on. All right, but before we do that, let's actually practice with our Bohr equation and our Rydberg equation to actually do some calculations. So what we're going to do here is we're going to calculate the energy and the wavelength of a line in the spectrum of hydrogen that goes from n equals 4 to n equals 6. All right, since it asks for the energy first, we're going to actually calculate that first. Now, I'm going to calculate that with Bohr's equation, which is something you're provided with. We're not expecting you to have this memorized. So it's negative 2.18 times 10 to the negative 18th, and it's joules. And then in parentheses, I have 1, and it's n squared and n squared. Now, interesting thing is, it's specifically, this is the final n, and this is the initial n. But what's interesting is if you get those backwards, you're just going to have the sign wrong. So don't worry about having those perfect yet. But we're going to do it right here. So we're talking about movement of electron from the 4 to the 6. So 6 is our final. So I'm going to plug in here 6 squared, and here will be 4 squared. And I'm going to let the calculator do all that work for me. So, and how about this? I will do 6 squared is 36. So 36 to the negative 1 minus 4 squared is 16 to the negative 1. All right, that's my parentheses. So I'm going to take my parentheses, I'm going to multiply it by 2.18 times 10 to the negative 18th, and then I'll just flip the sign. So my delta E is 7.57 times 10 negative 20th. And it will be joules. All right, that's the energy. All right, talking about wavelength here, we actually kind of have 2 ways to calculate this based on what we just did. But since it is asking for wavelength, I'm going to do Rydberg's equation so we can see how we'd set that up. So Rydberg's equation has 1 over lambda. It's 1.096776 times 10 to the 7th per meter. And then it's 1 over n 1 squared minus 1 over n 2 squared. Not necessarily n initial or n final, because the weird thing is if you do this backwards, you end up with a negative wavelength, and wavelengths can't really be negative, so you just flip the sign. All right, now common mistake here is everybody forgets to do the inverse here. And the other thing is watching the units, because it does say here it wants meters, so we're not going to have to do any conversion of the meters when I'm all done. But you got to have to watch out for that most times. So let's see what we get if we do this. So 1.0096776 times 10 to the 7th times, in parentheses, and it's the same numbers, so uh, 36 to the negative 1 minus 16 to the negative 1, and then close those parentheses. And I get this. Biggest reason I got that is because I probably should have put 4 and then 6, but I don't care. I can flip that sign when I write it down on the paper. But this is not my answer. It's not saying there's 380,000 meters for the wavelength, because this is equal to 1 over lambda. So I need to inverse this answer and then flip the sign. So this answer in meters, the wavelength is 2.63. And it was times 10 to the, was it negative sixth meters. Now watch out, sometimes it'll ask for the answer in nanometers, so you just take that and multiply it by 1,000,000,000. So watch how we ask for it. And you do see wavelengths in every single prefix there, because it's sometimes easier to see. If you think about this with that negative scientific notation, it's much easier for most people to talk about this in micrometers, because then we're getting rid of that number, that negative, that scientific notation. But that's how we would do something like that. Now, if I'd asked for frequency, so if I'd asked for the frequency of this, that's kind of interesting, because this gives you delta E. This equation gives you wavelength. To get the frequency, we have two strategies. We could actually take this energy and relate it to frequency with Planck's equation, or we could calculate this wavelength and relate it to frequency using the speed of light. Turns out either one of those will give us the exact same frequency, because we are talking about the exact same relationship. So if I give you a question and ask for frequency, you can calculate the energy and then get the frequency, or you can calculate the wavelength and then get the frequency. But they're all interchangeable. They're all related to one another. All right. Quantum theory is where this gets to be really chaotic. Now, we're not going to see any of the equations that apply to this, mainly because this gets very complicated very fast because of the sheer nature of what's going on. Now, what I mean by the sheer nature, we can actually relate it with something kind of cool. Louis de Broglie, ages ago, so shortly after Bohr came up with his theory, which was ages ago, he actually came up with this whole idea that the reason Bohr was finding those very limited integer sets, so integers of n, 1, 2, and 3, is because he was kind of finding somewhat related to the wavelengths of an electron. So what I mean by that, instead of this being n of 1, 2, and 3, 4, and 5, these values here, de Broglie said, well, maybe this is somehow related to the wavelength of an electron. And this is the wavelength, or twice the wavelength of electrons, and 3 times, and 4 times, and 5 times. And he actually said it was something like this, that peak of a wave, the top part of the wave, if you go around that circumference of a path, it needs to start at the same point it ended. So that's why they had to be complete wavelengths. All right. Well, that would limit you to integers, because a wavelength is fixed in length, and it would just be 1 wavelength, 2 wavelengths, 3 wavelengths. And if we define it as a standing wave, it has a start and end at the same point, that would make sense. So de Broglie is onto something here. But that would mean electrons in the atom are behaving like waves as well. And that really caused problems with those early scientists, because at this point, this is long enough into our understanding, we knew exactly what electrons weighed as. We knew their weight. We knew what their charge was. We knew for sure electron is a particle. So how can a particle definitely have wave-like properties? All right, so we're going to do something crazy. Remember that slit pattern thing that we did with lights? Turns out, if you change that light to electrons, you get the same diffraction patterns, or, well, related to it. You actually get that positive constructive interference and destructive interference from electrons. So, turns out electrons do have wave-like properties. This is really the technique, or the study they did that proved to them that light was a wave and a particle. Because here was something they knew for sure was a particle. It had a mass. They know for certain it's a particle, and yet it has wave-like properties. The only way we can explain this is if it goes through diffraction, just like our interference patterns is with our constructive and destructive interference. All right, so now that we know electrons are waves, we have to start looking at them as if they're waves. And we have problems with that because, all right, this Heisenberg, I know you've probably heard the whole idea of the Heisenberg uncertainty principle, and there is an equation for it. But I want to talk about it as to what it says. Now, we're talking about things that are ridiculously small. Electrons are very, 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 very tiny. Even on the atomic scale, if you compare it to the nucleus, it's the fraction of it. Even on a hydrogen atom, the electron that's around there is 1/1000th the size of the nucleus, yet it occupies most of the space. So let's actually think about this like our football field analogy we did when we talked about it. So nucleus is a little tiny thing, and there's one electron running around that empty space. Well, let's put it on that scale of a football stadium, and let's say you, for instance, as that one electron. If you're out in a football stadium and you're randomly running around, how are we going to measure both your speed and your position, momentum and the speed, without influencing one? What I mean by that, let's say this is the path you're going to take, and we're just going around kind of crazy. If I want to measure how fast you're going, I need to actually mark a start and a finish, right? Well, I'd have to count on you going through them, that start and finish, and I'd also have to count on you going through that that start and finish right after one another. So I'm all screwed. The results will be all screwy if for some reason you went and then this. So I would have to put restrictions on your position to measure how fast you're moving. Now, that's a concept based on a stadium. Only thing that Heisenberg did was, instead of saying it like that, he actually talked about using Planck's constant. He put it into his equation, and he did a probability map. So if you have all that space that you could probably be at, what's the chances you being exactly where we need it to be? And when he actually does that calculation, he sees something kind of interesting. At the atomic scale, with how fast the electron's moving, I'm going to erase my picture because this is actually a better way to actually think about this for what Heisenberg said. So here's the nucleus. Here's what we think the size of the atom. All right. If we're trying to study the speed of the electron and the position of it, so the momentum and the position, if we know for sure what its momentum is, how fast it's going, its position could be way out over here or over here. It is mostly in here, but there is a small fraction of a chance it's totally somewhere else. Matter of fact, it actually has a slight probability that even if we're talking about a molecule on your computer screen, there is a slight possibility that an electron for that molecule is on the other side of your room. Not high probability, but it's a chance. And Heisenberg actually was just able to show this because he wanted to point out that it's impossible to study them both simultaneously. We have to study on average. And that's what we end up doing on most of these cases. We don't study the electron always. We just make a bunch of studies and throw that all together and look at where we found the electron most of the time. So it's a probability. All right, but before we do that, we got to actually, how are we going to study this? So we have to bring all of those little things we talked about. So Planck's model and Einstein's model and Rydberg's model and Bohr's model, and put it into something with what de Broglie just said to map all electrons simultaneously. And we have to keep in mind what Heisenberg just said, who said we can't study them all simultaneously, or we can't study their position and their speed simultaneously. All right, so ages ago, bunch of these scientists went to this guy Schrodinger, who's just a mathematician, and he said, and they basically went to him. All right, we have an atom. I got to draw on my screen, and we know it's a wave that has a start and end point, and it must be standing, so it's got to have a definite start. It's going to start right at that point. It's going to go over here. The wave's going to look like something between the two, and it is going to be in 3 dimensions. And we want to some manipulations of it, and that almost is all he was given. A very vague thing, but he knew what he had to map because he knew the limitations based on the other things, and he knew that it wasn't going to be a perfect model because we're just going to use it to study where the electron is likely to be. All right, so Schrodinger equation turns into something that looks kind of like this. Now, the weird thing is, what I have at the bottom of the page is not the Schrodinger equation. It's the mathematical operation we're going to do to this magical wave function that Schrodinger comes up with to actually get the actual energy at that particular level. So you remember how Bohr told us that if we had our little levels, we could calculate the change of energy, so we can get this delta E. Well, Schrodinger's equation for this wave function and this Hamiltonian would calculate the energy at this level, and then we could calculate it at that level. So he actually gave us a method to calculate the actual energy levels for a fixed state, like the ground state. Now, we had some manipulations to it because you look how crazy this is. We got to talk about that particle moving in 3 dimensions, and we actually knew that the wave function varies. So it gets kind of complex, which is why we don't really ever do any of this calculation on paper. This is done on supercomputers, even to this day. Some of the fastest computers on the planet are just doing quantum theory calculations. All right, so we're going to actually talk about what we're dealing with here. So turns out that that wave function that we're talking about, that little lambda, is going to be affected by the energy level. And we're going to say that's affected by an n. The n is just an orbital destination. It's telling us the energy level of that particular wave function. You can kind of relate it to the size of that energy or how far it is from the nucleus. They all kind of mean the same thing. That's why this picture kind of looks like planets orbiting. But it's probably not right to think of it totally as a sphere, because it turns out when we actually fully model and map what the wave function itself looks like, what Schrodinger's equation looks like, it ends up looking something like this. Now, up here is the equation that Schrodinger found to apply to just hydrogen. So look at all this crazy stuff. And there are 3 variables he had to put into his equation, and that's these things right here. So the first one is talking about that energy level. How far are we going to, how high are we going to let the electron go? So what shelf's it on? And it is just an integer. This is 1, 2, 3, 4, 5, 6, 7, 8. And this is that n we just saw. So Bohr's n, Heisenberg's n, that is this first value. The larger it gets, the more energy is in that orbital. All right, but what happens is that's almost like a sphere, but we can put little folds in that sphere. And that's what these other two, they're actually talking about how we do the folds. So what I mean by a fold, let's picture a circle or a balloon or something. When we talk about a fold, we really are going to say, I'm going to take this side, twist it this way. I'm going to take the other side and twist it the total opposite way. Make sure I draw that. And if you think about that, if it's like a balloon, if you take 2 sides of a balloon and twist it in opposite directions, it folds right in the middle. You make a little figure 8 out of it. Well, Schrodinger was showing us that those wave functions do the same thing. We can twist a wave and cause it to actually put a little node into it. It actually does fold over on itself. And that's what this second one does. It actually wants to know how many nodes you put into it. And that's what we're seeing here. So if you see up this one, that's a energy level of 2. It looks like a ball. But if I put a fold in it, it cuts it right in half. Now, right below that, we have the exact same thing. You see how these two look exactly identical? Well, they are. It's just that we have the fold differently. So on these two, we have one where I did the twisting on the left and right. And on the other one, the twist was done straight up and down. So there's different ways or orientations we could actually do that. And Schrodinger says that needs to be part of the equation because we are actually trying to do this wave in 3 dimensions. So where you make those twists are different. And that's what all these pictures are, is how you can actually make these different twists at different levels. And it is chaos almost, but there is a little pattern to it. And we're going to try to make sense out of this pattern. So that's why we had this picture in a circle, because it introduces the second quantum number that we're going to add. So we're going to end up with 3 quantum numbers that explain an actual atomic orbital. That first one was just the energy. So it is the bookshelves that Bohr actually told us. All right, but Schrödinger was actually saying when we go up on these levels, we can actually have more folds. Like this lowest level, n equals 1, it doesn't have any folds. It's always going to look like a sphere. But on my n equals 2, I would have the possibility of being a sphere. I also have the possibility of having 1 fold in it, which is why I draw the little figure 8 where I twisted it. On the third energy level, I have the ball, I have the figure 8, but now imagine this balloon like this. So it's got that node in the middle, and we're gonna twist it across that. So we're gonna get something that also looks kind of like a clover. Has 2 folds in it. All right, so that shape happens because this L quantum number causes folds to happen. It folds in there. Now, Schrödinger wants to do this not by what does it have folds. He wants a little number to represent the number of folds. So we have an L of 0, which is no folds. They all look like balls. L of 1 has 1 fold, so it looks like that figure 8. L of 2 has 2 folds, so it ends up looking like a clover. There's other shapes that pop up, but the whole notion of it, the L is telling you how many different ways you fold it in on itself. And there is more. So technically the L value goes up to infinity, but the maximum it can be, the L always starts at 0, and the highest it can be, so the maximum it can be, is L equals n minus 1. So if I have an n equals 4, the most number of folds I could have is 3. If I have an n of 20, the largest the L can be is 19. It's always 1 below because you always have no folds to start. Okay, now, I already introduced this weird concept that I could have folded this one in 2 different directions. So we're going to have to talk about this weird possibility that since there are other ways to fold it, there are other orientations. Well, Schrödinger actually figured this out too, and he put this m sub L number in. So the number of orientations is an odd number. It's geometric. And what I mean by that, if you have that L equals 0, so the thing that looks like a ball, there are no folds, so he just decided to say there's only one way we can do that. When L equals 1 and we have the little figure 8, there's actually 3 ways you can do that. When L equals 2 and you look like the clover, there are 5 ways to do that. L equals 3. I'm not going to try to draw the picture, but it kind of has 8 nodes. There are 7 ways to do that. L equals 4, 9 ways. L equals 5, 11 ways. Notice how it's going up by odds? Well, that's just a geometrical property of how those folds go. It always goes up by odd number. You add 2 more to each one. So Schrödinger, who understands, as a mathematician, understands the geometry, he wants a numerical value to assign to that. So what he did was he decided that he's going to have his m sub L, in every case, I'll put it over here, m sub L has the smallest value of being negative of whatever your L is, and it goes by integers all the way up to positive of whatever your L is. So here on L equals 1, your possible values of your m sub L are negative 1, 0, and 1. And here at 3 would be negative 3, negative 2, negative 1, 0, 1, 2, and 3. And that's where all 7 values come from, negative 3 all the way up to positive 3. Now, he did that just to get numbers. Now, this is kind of weird, though. It actually tells us that those 3 quantum numbers that we actually defined to actually define the orbital, the n, L, and m sub L, are all integers. And backing up to this picture, that's what these are. That first quantum number is talking about the energy level. The second one's talking about the shape. And you'll notice if it's got a 0, they all look like balls. They're all perfectly round. If it's n equals 1, it's got a little node in the middle. It's got almost like a top and bottom, almost a top and bottom, almost a top and bottom. When the uh, L is 2, we start to get different looks. And then the last one is really just talking about the orientation. You typically can't see a difference. That's why this one right here and this one right here look identical, just rotated. It's because they are. Their orientation is the only thing that's different. Okay, so putting these all together, we're going to have these three numbers. That gets to be a little bit confusing. So something that we end up seeing a lot more is that second quantum number, the one in the middle. We turn it into a letter sometimes. So L of, and that's what this line's about, L of 0 we say is an s orbital, L of 1 is a p orbital, L of 2 is a d orbital, and L of 3 is an f orbital. And that would give us the ability to go back to this thing and say, well, this is a 2s, this is a 2p. Now we're ignoring this when we call that. We're just saying the first quantum number gives us the number. The second one tells us the shape. So 3p, this down here is a 4s. So it just actually helps us to not have all those numbers repeating. All right, so shapes for our diagrams. We have on each level more and more shapes, and we have L's up here. So I have an L of 0, I have an L of 1, 2, 3, 4, 5, and 6. But I don't have all those on each row. So what I mean by that, if this is the ends, or these the end values, for n equals 1, I only have one shape available. So there are 1s orbitals. On the second row, there are 2s orbitals and 2p orbitals because I have the two shapes. N equals 3, I have three shapes, so it's 3s, 3p, 3d. We can keep right on going. It's just going to add one more as we get here. Now, I only said S, P, D, and F. It's interesting. After that, they kind of go alphabetical, at least for a little bit. So my next thing here is actually a 5G orbital. And then after G is H. After H is I. And then we're going to go on and have our 8. Now we're going to see something interesting. We're not going to actually have anything at all talked about with these G's. We're not even going to talk about it, well, even what they look like. Now we know it has 4 nodes in it because the L equals 4, but we're not going to talk about them because nothing in nature uses them. Now, even the man-made ones. So we have on the periodic table element 118. We likely will not have to deal with anything in the G orbital, at least in the ground state, until we get up to element 120. And as far as I know, we don't even have anybody who's gotten a suspicion that they made that molecule or that atom. So we're not even really going to talk about it. It's just there. It's higher level. And it's almost up near where that infinity bar was on Bohr's model. So it's actually very far away from the nucleus. All right. Now, along with that, our orientations for shape, we already kind of talked about this. So when we're dealing with an s orbital, doesn't matter what the n is here, we just really have that sphere, and there is only one. So you're going to see that a lot of times when we're talking about an s orbital, we're going to draw a little box or a line, and we're just going to put an s underneath it. Now, p, there was the little figure 8 thing, but there were 3 ways to orient that, so we end up drawing 3 boxes to represent the 3 p orbitals. And D, I'm not going to bother to draw that, but we're going to have 5 boxes. And F are 7 boxes. And if we actually were to draw a G, it's just going to be 9 boxes. And those boxes represent all those possible quantum numbers. All right, now we're going to combine all this, not so much with that, with this concept. So I'm going to actually, using the n equals 4, come up with all the possible orbitals that exist in that shell. So we're going to break this down, what I mean by all the possibles. When I have an n equals 4, I have 4 shapes available. I can have S, I can have P, I can have D, and I can have F. All 4 available. Now what that means is, have an L possible of 0, have a possible L of 1, I have a possible L of 2, and I have a possible L of 3. All 4 of those number of folds are possible. Now, right here, when I have an L of 0, my only possible M sub L would be 0, because we have that nice little relationship that the M sub L goes from negative L to positive L. And if my L was 0, the only thing that's possible is 0. But my P orbital, I have an M sub L of negative 1, 0, or 1. And on D, it's negative 2, negative 1, 0, 1, and 2. And on F, it's negative 3, negative 2, negative 1, 0, 1, 2, and 3. All right. Every number up there gets related into our nice little brackets, we're going to say, to represent an orbital. So this whole, just that one, would have an orbital description of 4, 0, 0. 4, 0, 0. These 3, it's 4 because of that 4. It's 1 because of this. And we have negative 1, 0, and positive 1. On this, we have 4, 2, negative 2, negative 1, 0, 1, and 2. I'm out of space, but parentheses. And so I don't do that again, run out of space that is. I'm just going to actually write them over here. So I have 4, 3, and negative 3. 4, 3, and negative 2. 4, 3, and negative 1. No. 4, 3, and 0. 4, 3, and 1. 4, 3, 2. And 4, 3, 3. So n equals 4. The total number of orbitals I have is 7 plus 5 plus 3 plus 1. 7 plus 5, 12, plus 3, 15, plus 1, 16. So 16 orbitals possible. All right. Turns out, when we start filling all those orders, we see orbitals, we see something interesting. So what I have here is I have the 1s, then I have 2s, 2p, 3s, 3p, 3d, spdf, spdf, spdf would be up here. So I don't have all of them, I just have the first several. All right, but we have an interesting dilemma. If you look at the 3s, for instance, I go from S to P to D, but technically I didn't start filling this D until after the s orbital was full. So it's kind of interesting. When I'm starting to put electrons in here, let me erase what I put on here. I will have, and what I'm going to do instead, I'm going to say we're going to fill the 1s orbital up, then we'd move up and fill the 2s orbital, then we'd fill the 2p, then we put electrons in that 3s orbital, and then the 3p. But before we fill the 3d orbital, we put some in the 4s. S gets filled, and then we fill the 3d. And then 4p, because that's the next highest. And then we're back here to 5s. All right. You notice how this kind of looks like it's jumping back and forth all of a sudden? Well, it is. But it has to do with the fact that we're getting more and more energy into these orbitals because all those nodes we put in there. What we need is a way to predict how it's going to fill. Well, all we're going to do to predict it, we can actually redraw something like we did here, a little table, and this actually does tell us how they fill. I know it doesn't look like it does now, but what we're going to do to explain how we fill them is we're going to actually draw little weird diagonal angles going backwards. So we fill the 1s, next thing is the 2s, then 2p and 3s. Then come back up here and 3p and then 4s, and then the 3d. And then there's the 4p and 5s back up, 4d, 5p, 6s back up, 4f, 5d, 6p, 7s, and then 5f, 6d, 7p, and what do you think is next? Well, it would be whatever's here, so it's going to be up 8, and that would be s. And then we're backing all the way up here, and we'd be coming down. The 5G is over here. We're not hitting that yet. So the next thing we'd be actually hitting, oh wait, no, we would be, sorry, I put this too far over. Next thing we would be actually hitting is the 5G. So that after the 5G, we'd have our 6F, and then 7D, and then 8P, and then 9S. So we could predict what happens next by looking at this thing. We call it the Aufbau principle because it helps us understand how they fill. Now, as cool as that is, turns out the periodic table does this as well. And ironically, I forgot to actually load up the periodic table. So let me get it here quick enough. And move this to our page. All right, so periodic table actually does tell us how these fill, but we have to take in consideration something weird. We will sometimes hear group 1 and 2 referred to as the S block. These guys over here are sometimes called the P block. Then we have the D block and the F block. Now, the reason that calling it that helps us is that we see as we go across, we're going to fill up the S orbitals, then the 2s, 2p, 3s, 3p, 4s, and then we get to our first D row. And even though it's in the fourth row, it's actually the 3Ds. So that's a 3D. Then we're back to the 4p. So we can let our periodic table show us how our electrons fill. All right, back to this. All right, last quantum number. We have one more quantum number. The first three that we had, which was N, L, and M sub L, define the orbital. But when we put electrons in that box, we're going to identify the electrons with an M sub S. And there's only two possible values because we can only put 2 electrons in an orbital. And the orbital can be spinning positively or negatively, which is why you will sometimes see when we draw a little box, if I said this was an S orbital, you might see it drawn with an arrow up and an arrow down. And that's representing the 2 electrons. They just have to be spinning the opposite direction to fit in that same orbital. Schrodinger needed a number in there. So the M sub F's values that we use are, and I'll put them over here, -1/2 and +1/2 for upspin and downspin. All right, so let's expand that to something. Let's say I wanted to actually calculate the max number of electrons in a particular shell. We'll start with n equals 2 and see if we can find a nice little pattern. So when I have an n equals 2, and rather than draw out the quantum numbers, I'm going to put those little boxes in there. When n equals 2, I can have an s orbital, which I would call 2s, and since it's 2, I can have 2 shapes. So I'm also going to have the 2 p's. And in the p's, we always have 3 boxes. All right, each one of these boxes could hold 2 electrons. So my n equals 2 has 8 possible electrons. All right, let's do the same thing if we have n equals 5. If we have an n equals 5, we have 5 possible shapes. We have 5s, and we have 5p, and we have 5d, and we'd have 5F. And I'm out of space, so I'm going to put it down here. 5G, and there's 9 of these. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. And we could put 2 electrons in every single one of those. So count up all those boxes. Why I come up here and write something kind of neat. Number of electrons. Excuse me. Turns out there's something nice about this pattern. Since the number of electrons always goes, or the number of orientations always goes up by 2, it's a nice little exponential growth. So the number of orbitals is always just the n squared. So n squared on n equals 2 tells me that there's 4 orbitals, or 4 boxes grand total. When it's actually n equals 5, I actually have 25 boxes. And then to figure out the number of electrons, you just double that. So when it is 25, or when it's n equals 5, there is actually 50 potential electrons that can go in that orbital. All right. Cool as that is, where we really apply this in what we're going to do nowadays is actually help us to understand what's going on with more valence electrons. Now, to do that, we're going to look at electron configurations, because we're going to see that's a little bit more informative than just the valence electrons. All right, when I talk about electron configuration, we really are going to talk about what type of orbital the electron's in. So on a hydrogen atom, for instance, all those electrons are in a 1s orbital. And we know that because on the periodic table, that's just right there. It's the first row, it's an s orbital, so the electron's in a 1s orbital. And we would actually say 1s, and then we'd say how many they are as a superscript. Therefore, if we went to helium, for instance, helium, we're just going to have a 2. And along with these electron configurations, we also have orbital diagrams, which are just boxes representing the orbitals. And we'll just put arrows in there to represent the electrons. They both say the same thing, that 2 tells us the s orbital is full. The box shows us the s orbital is full. Now, if we go to something like carbon, for instance, our electron configuration gets a little bit more advanced. So carbon is just a little bit further down the periodic table. So our s orbital in the first row is totally full. So we'd say 1s2. Then we have 2s2 for the lithium and the beryllium electrons. And then there's just 2 electrons in the p block. So we have 1s2, 2s2, 2p2, which is where that comes from. But when we actually draw the orbital, or the electron, the orbital diagram, and we put a box for each one of these, we don't just put one box for the p, we're going to show all of our p's. So we have all 3 boxes drawn. Even though we only got 2 electrons in there, we're going to draw all 3 boxes. And the other thing that we're going to do is we're not going to pair up the electrons in those 3 p orbitals until we have to. So since these orbitals are all the same level and they're all equivalent, we're going to keep the electrons separate until we can't, which is why they're drawn like that. All right, let's go up one. Let's go to something more chaotic, like a sodium. Now, the reason I say chaotic is because it's just further down the periodic table. You'd have everything in that top row full, everything past carbon full, so the 2p would be full, so 2p6. Then we'd have just the 3s1. Well, as you can imagine, when we get further and further down the periodic table, it would take a very long time to write the electron configuration of, say, lead, because of all those previous orbitals that are full. And the other thing, it would take up a lot of space on paper. So what we're going to start seeing along with that electron configuration is a condensed electron configuration. And what all that means is if we were looking at something like sodium and we want to do an electron configuration, we're just going to back up to the next previous noble gas, which is neon. And so when I do the electron configuration of sodium, I put neon in brackets to say it has all those core of electrons of neon. And then it also has just the s orbital. So these two things say the exact same thing. So the valence electrons are just the things that weren't in the noble gas, and the core electrons are the items that are in the noble gas. All right. I just talked about lead. Let's actually do one of our bigger ones. We're going to do phosphorus. It's not much bigger than sodium was. It's just right here. All right, so I have two ways of doing this. To see it the crazy way, or the preferred way, we're actually going to just start at looking at phosphorus on the periodic table and back up to the previous noble gas. So phosphorus, previous noble gas, is neon. And after the neon is filled, we're at right there on the periodic table, we're starting with where sodium is. So we have all the electrons in the s orbital in the third row, 3s2. And then we're going to skip over to 3p, and phosphorus has 3 electrons in it in the p block. And that would be our electron configuration. Our orbital diagram, here's the nice thing. Orbital diagrams, we typically don't draw boxes to represent the core electrons. So we would only need to draw that one box to represent a 3s orbital, and I normally draw these slightly higher up to show it's slightly higher in energy, and I'll be drawing it as the 3p's. Those 2 electrons go right here, and the 3p, 1, 2, 3. Okay, that's the electron configuration and the orbital diagram of phosphorus. But if you read the rest of that, it wants us to draw the 4 quantum numbers for the last electron added. And in this case, it was that one right there. That's the last one I drew. All right. We know 2 quantum numbers, no problem, because that's in a 3p orbital. So we know that that arrow must have an n of 3, and a p tells us that the L is, I'm starting to draw a -1, is a 1. So we have a 3 and a 1. We have to come up with the other 2 quantum numbers. All right, this is where this gets interesting, because when we draw our boxes, we're not trying to draw them in any particular order, because we can't tell the orientations apart from one another. We just know they have to be different. So here's something interesting. If I were to give a question like this on a multiple choice test, I actually have 6 possible answers. Excuse me. Because my m sub L can be anything from -L to +L. So I could have that as -1, 0, or 1, and it would be perfectly acceptable, because I can't tell what the orientation of that box is. It's just a box. I know it's different than those other 2, but I have no idea what it is. And same with the spin. It's either that -1/2 or that +1/2. But I can't tell from just that arrow. Yes, I drew it as an up arrow, but that was because I draw up arrows before I draw down arrows. There's no reason to say that the atom chooses one over the other. So if I were to ask a question like on this and ask what the 4 possible quantum numbers are of that last electron, there are 6 potential answers, because the last 2 are just restricted by the rules set up. So the L tells us what the m sub L has to be, or what the possible values are, and the spin can only be positive or -1/2. All right, so let's do another one of these. We're going to do the electron configuration, this time of xenon. Now, I chose xenon to actually create a little bit of confusion, because being a noble gas, you might think, well, since it's a noble gas, we can say its electron configuration is a noble gas. And it kind of seems reasonable, because we said that was a safe thing for a condensed structure. Turns out we can't do that because the rule actually says if we're going to do our condensed structure, we use the next previous noble gas. So that's what we're going to do. I'm going to erase this. Xenon, to actually do it, I need to back up on the periodic table to the next previous noble gas, which is krypton. All right, after krypton, 1, 2, 3, 4, 5. 1, 2, 3. Krypton is in my fourth row. So the next thing after krypton is I'm going to put some electrons in a 5s orbital. Now, after the 5s orbital is filled, I go to the 4ds. I don't hit any p orbitals until the next row down. On your periodic table, you see a thicker line. That's where the f orbitals go. And between strontium and yttrium, which is where we're at in the fifth row, there is no thick line. So it goes from the s right to the d's. And then we have our 5 p's, and yet there are going to be 6 of them. All right, on to the orbital diagram, because it's going to help us see something interesting. Now, in the orbital diagram, we're definitely always going to see the valence electrons. So I would actually ask now, and then we'd have to back up to previous chapters in chemistry, how many valence electrons does xenon have? And even back in intro, we said it was 8. And that's actually where we came up with that weird thing for our Lewis diagrams and Lewis structures of the octet rule. Yet, which of these, in this, how I drew this electron configuration, are the valence electrons? Well, it's kind of neat. The valence electrons always count those outermost electrons. This is definitely core, because that's the previous noble gas, and there's nothing we're going to add to it. The core electrons are always those that go from in that previous noble gas. The valence electrons are always the s orbitals, and any other orbital that's not, well, s and p orbitals are definitely valence, and any other orbitals that are not full. So if the d only had 9 electrons, we count those as valence. But since this is full, has all 10, we don't count that. That's not a valence electron anymore. So it's kind of interesting, since we only count the s and the p's as valence, we only draw those for our orbital diagrams. So I'm not going to be drawing the 10 or the 5 boxes that represent those 4d, because I don't consider them valence electrons. So xenon has just these 8 valence electrons. All right, let's do something kind of weird. The electron configuration of an ion. Now, if I were to ask you how many electrons the sodium ion has, most of you can look at the periodic table and say, well, it had 11. That positive means take away, so it has 10 electrons, and it should have an electron configuration the same as neon. And same with phosphorus. Phosphorus gaining 3 should have the electron configuration of argon, because that's what it moves up to. So you might think you can just do the electron configuration of neon or argon. But we're going to see that's not quite right. So what we do to come up with the electron configuration of ions is at first draw the electron configuration for the atom in its ground state. Now, we already saw sodium. That's why I chose this one. Sodium has the electron configuration having neon, and then a 3s orbital with just a single electron in it. And phosphorus, when we did that, also had neon, but it had 2 electrons in the s orbital and 3 electrons in the 3p orbital. All right, so that would be the electron configuration of those neutral atoms. This positive means we remove an electron. Now, old way, we would see the neon and then 3s 0, because they're stressing that there was an electron in the s orbital and it went away. Nowadays, what you'll typically see is just neon in brackets. But it is in brackets, and it's just that, the neon in brackets. And phosphorus, rather than go up to argon, we actually draw the neon 3s2, and then we put those other 3 in there, so this becomes 3p6. So do the electron configuration of ions, do it neutral, and then add or remove the electrons from the orbitals you need to. All right, on to some periodic properties. Now this is getting away from the electron configuration. It is just flat out looking at the periodic table and predicting the size, the ionization, and the electron affinity. All right, so we got to define what we're talking about here. Atomic size is probably the easiest one to think of these three, because it really is talking about the size of the atom. Now on covalent bonds, or the nonmetals, we're looking at the covalence bonds and dividing that bond in half to come up with the radii. For the metals, we really are looking at a metallic bond and doing the same type of thing. Well, down in that bottom picture, we're getting the general size drawn pseudo to scale, and it's hard to see what's going on here. Much easier to say if we were to actually do something like this. So we have the radius as a number on a graph, and we're comparing it to the atomic number. So it is just an integer on the bottom, but it's the number of protons. And we're seeing something that we might predict. We're seeing the purple ones here at the top are just those group ones. So lithium is smaller than sodium, which is smaller than potassium, which is smaller than rubidium, etc. So on the periodic table, we really are staying as we go down, it gets bigger. Lithium is smaller than sodium, which is smaller, so it gets bigger as we go down. But what we see that is very odd, going from left to right, we get smaller. So it turns out lithium is actually bigger than neon in its same row. So let's go back to the periodic table and see what that says. That's saying that lithium, which has a mass of 6 AMUs, is smaller or is larger than neon, which has a mass of 20. So the size gets bigger as we go from right to left and from bottom or from top to bottom. So the largest atom on the periodic table is actually francium, and the smallest is actually helium. And that does apply here. So even though, well, I'll go up a row to some things that really exist. Cesium, which has a mass of 132, is actually bigger than bismuth, which is the last one that has a real mass, which is 208. Even though it is heavier, cesium is bigger. Now, it turns out we can relate this to quantum theory. This makes sense if we think about this as a quantum theory problem, because technically lithium is the very first thing that it's got one more electron than a noble gas. So think about lithium as being helium and then a single electron in the next orbital, 2s1. That too is a whole nother bookshelf. So helium had everything it needed on the lowest bookshelf, the n equals 1 level. To actually put that next electron in, we needed to move up to a whole nother bookshelf, and we're only going to put one little atom on there. So it's almost like if we're shipping eggs, this is the dozen of eggs, and if you buy 13 eggs, you'd have a dozen eggs in just one container of just one egg. A lot of wasted space. That's what we're seeing here. Lithium, sodium, potassium, rubidium, and cesium are huge in size because they have just one electron in an upper level orbital that's totally empty, except for that one electron. The entire shelf is empty. So the reason it drops is because we're getting more and more efficient packing. Matter of fact, neon still has electrons just in that second shell, so the 2s and the 2p, but lithium had to create the shell. It's just mostly empty. Neon has that shell completely full. But we're going to say it much easier to actually just say this. If I have the periodic table here, the size does something like this. It gets larger as you go towards francium. All right, next thing we're going to look at is the ionic radii. It's not really a periodic trend at all. Matter of fact, it's nowhere near a periodic trend because ions are gaining and losing electrons. Now, aluminum, for instance, turns into aluminum plus 3, very, very stable. And if you look at the periodic table, you're going to be able to see that its electron configuration is just going to be neon. And the electrons that were in the 3s orbital are now gone, and the ones that are in the p orbital are now gone because that's where they came from. All right, but more importantly, Al3 plus has the exact same electron orbital as neon. And neon, being on the total opposite side of the periodic table, it should be very, very small. All right, so interesting. When you actually want to come up with a relationship with ionic radii, you look at the noble gas they've been turned into. So, like aluminum gets turned into neon for the noble gas. If we look at the periodic table, so does Mg2 plus, and so does Na plus. So it turns out all three of these would have the exact same electron configuration, which would just be neon in brackets. So it turns out those three have a size more closely related to neon than to themselves individually. And they won't be the same because even though they have the exact same shelf setup of neon or the exact same orbital diagram, this thing has a bigger nucleus. That bigger nucleus will pull it in more. So this thing's going to be the smallest, and this one's going to be the largest. So if I want to rank my ionic radii, I figure out what noble gas they relate to, and then I just flat out say that the charges are the order. So I would rank them by their charges, and I'd say the more positive one is the smallest. And I can include negative ions in here. So after we get to neon, we'd have fluoride as a negative ion. It's actually going to be larger than sodium positive ion because it's got a smaller nuclei. A smaller nuclei pulls those neon electrons in closer, makes the whole atom bigger. All right, so let's rank all these. So I have a whole bunch of them. My first step really is to see what noble gas they're related to. So nitrogen with 3 extra electrons is going to be like neon. Oxygen with 2 is going to be like neon. Fluorine is going to be like neon. Neon is a neon. Sodium is going to be like neon. Magnesium is going to be like neon. And aluminum is going to be like neon. And what I'm doing there is on the periodic table, nitrogen with 3 electrons, 1, 2, 3, is neon. Oxygen with 2, 1, 2, is neon. Fluorine with 1 is neon. Sodium, remove 1, neon. Magnesium, remove 2, neon. Aluminum, remove 3, neon. All right, so all of these on this page are what we consider isoelectronic. They have the exact same orbital diagram as neon. Their electron shell looks exactly the same as neon. All right, so if I want to rank these, I flat out can actually compare every single one of them to neon. I just say that the most negative one is the largest. And the reason I say that is because it has the smallest nuclei, and that small nuclei pulls in on those electrons the least. So these electrons are able to get further out. And we really do just rank them by their charges. All right, second to last thing in here in this chapter. First, ionization energy. Now, on the slide where we're talking about the periodic trends, it just said ionization energy. Well, that's too broad. Ionization energy is just the energy it takes to make an ion. First ionization energy is very specific. You have an atom. I'm going to put A here for atom. And we're going to remove 1 electron from it. If you remove an electron from an atom, that atom becomes positively charged, just a single positive. That's what first ionization energy is. Now, thinking about the periodic table, where on the periodic table do we find atoms that like to be positive 1 species? Well, that's easy. Everything here would like to give up 1 electron because then they're just like those noble gases. So my lowest first ionization energy should be group 1. All right, now, that's right. Among these, which one of these would probably give up the electron the fastest? All right. It's obvious it's either the top or bottom because the extremes, and you might think top because it's the smallest atom. But turns out the smallest atom has that valence electron we want to get rid of closest to the nucleus. So that one electron on hydrogen is really close to the nucleus. So to get that electron away, I have to get close to that nucleus. Yet on francium, that electron's way out far in the distance, and I don't have to get super close to the nucleus to get to it. So what we see is on our first ionization energy, they drop as we go down on the periodic table. All right, but if we look really close at this graph and compare it to the uh, if we compare it to the size diagram, we see the exact opposite. The smallest first ionization energy is francium. The largest is actually helium. So here's something interesting. If you know the ranking of your radii, you also know the ranking of the first ionization energy. It's just perfectly opposite. All right, last thing we introduce in this chapter is electron affinity. Now, electron affinity looks like it should have a trend because it almost looks like it's the exact opposite of first ionization energy. So electron affinity is you have an atom that gains an electron. Therefore, it must become a negative ion. All right, that looks very similar to first ionization energy, so it seems like it's something that should have a periodic trend. Turns out when we check it out, it doesn't really have a periodic trend. Yes, the one that is the smallest are these group 17, which like to become our noble gases if they gain one, but there's not really a easy to rank high. Matter of fact, the highest is actually chlorine right in the middle. And if we go left to right from it, look at that. We go positive for argon, go negative, get a little bit more negative back. So you notice there's not even anything close to periodic trend. We introduce that to define electron affinity, and then we just say there isn't a periodic trend here. So there's not something we can rank and say, okay, that's how it's going to behave all the time. All right, a lot of stuff in this chapter. I went through it way too fast. So nice thing about being on the internet, you can watch it again. Look at sample problems in your book. It's a good idea in this one to go through the actual chapter itself. And in the chapter are questions. Do those questions that are in the chapter as you go through the sections. That'll help clarify things. And almost everything else is part of a history lesson. Send me emails on any questions you have. Have a good evening.